Today we are going to, or actually before we start talking about what we're going to do today. Oh, also the screen apparently isn't showing, which is problematic for you all. I think I said that our exam was going to be on Tuesday of next week. That is no longer true. I'm aiming for Thursday of next week, so 1 week from today. Figure out what is going on. Okay. So regarding your exam, my expectation is for it to be 3 problems, effectively 1 problem on transformer related things, 1 problem on purely magnetic circuit related things, and 1 kind of in the middle, like we transitioned in the class effectively. Each problem will be worth 30 points, so you will literally receive a full letter grade by signing your name correctly. So please remember to do that, okay? Each problem will be broken down into multiple parts with the expectation that if you solve them in the order that I suggest that you do it, you should probably wind up getting the right answer or something close to it, and it'll give you plenty of opportunity and all that kind of good stuff to earn partial credit and all that jazz. Anything sound unreasonable about that? All right, so that's what our form, yes. 3 problems, each problem containing multiple parts. Don't know how many because I haven't written it yet, but that's my goal. All right. And that will be 1 week from today. Hugh.
Will there be a formula sheet of any kind?
Yes, you will be allowed a formula sheet, 1 page, front and back, handwritten. I do not have any particular preference as to what you put on said formula sheet, meaning you can put anything you want, but it needs to be handwritten by you so that one person doesn't write a really good equation sheet for the entire class and then distribute it. So I expect you guys to write your own. Any other questions regarding the exam? All right. So practical transformer model. So at the end of our last class meeting, we talked about ideal transformers, and there were a couple of assumptions that we made when we dealt with our ideal transformers. Particularly that our core permeability was infinite, so that all of our flux passed through our coils without any leakage, and that we had 100% efficiency, therefore no losses were going to occur. Today we are going to develop a practical transformer model that takes into account losses, nonlinearity, and things like that. So we're going to start by talking about where our series components come from. Actually, I'm going to start by drawing a little picture here. Okay. So let's see. I think I've been using blue for structures. So this is going to be our core. Because we have a transformer, we will have windings on both sides of our core, like so. And because we have a transformer, we're going to be dealing with RMS voltages, so that's why I'm labeling my voltage in the RMS phasor domain and my current in the RMS phasor domain. And this coil 1 is what we're going to call the primary, and it has a certain number of turns, N1. And then over here on the right-hand side, we will have a second coil. Over which our secondary voltage V2 will occur. This is our secondary current, I2, and we have some number of turns, N2, right? So we are exciting our primary coil by applying some voltage across the terminals V1 and observing a transformed voltage at the terminals of our secondary coil, coil 2. So our excitation voltage drives some flux around our path like so. So if we're dealing with practical coils here, we have to take into the account that our solenoidal coils that are wrapped around these cores are not infinitely long, and therefore some flux is going to escape. So we might see something like this. So not all of our flux generated by coil 1 flows through coil 2, and similarly, not all of the flux from coil 2 is going to flow through coil 1. So we have some amount of flux leakage, which we're going to have to take into account. All right, so we're going to start by identifying the series components of our practical transformer model. All right. So the first thing that we are going to take into account is that our transformer is made of wires, and real wires have resistance. Okay. So on the primary side, where this is our voltage V1, and this is our current I1, we are going to have some resistance RP. So this is the resistance of the primary windings, and it is due to the fact that our wire is made of copper, and copper has some small, but not entirely negligible all the time, resistance, okay? On the other side, we're going to have our secondary. And our secondary is also made of real wire. And so we're going to have some resistance RS. Here's our secondary voltage and current. Okay. So these resistances RP and RS account for the copper losses of our windings. So effectively, if we pass a current through those wires, they will heat up, and that transfer of electrical energy into heat has some associated loss that we characterize as a resistance. Okay. From our initial diagram, we can see that not all of the flux that passes through the primary coil links to the secondary coil and vice versa. This leakage flux is a form of inefficiency in the system, but does not represent a true loss, meaning we're not going to see any power losses because any energy that's stored gets transferred back and forth. So to best account for this leakage flux, we are going to include some inductive reactances. So we're going to have an inductive reactance Jx sub P in our primary, and an inductive reactance Jx sub S in our secondary. Like so. And let's go ahead and take care of these guys as well. So these are our series components. Now we're going to introduce our shunt or parallel components. Okay. So in addition to the copper losses in our windings, we are also going to have losses from our core. And we talked about these when we were dealing with magnetic circuits. We're going to have some amount of hysteresis losses, and we're going to have some amount of eddy current losses. We are going to lump those together with a single resistance R sub C, where this R sub C is representative of the core losses, okay? We place this resistor in parallel because it depends on the amount of applied voltage, okay? Our next component is going to represent the magnetizing current that is needed to magnetize our nonlinear core. So the fact that we have not perfectly linear core means that we have some magnetizing current. Experimentally, this current will lag the applied voltage by 90 degrees. And since we have a current lagging a voltage by 90 degrees, that looks like an inductance to me. So we are going to have, sorry, this should be an inductor. This guy is going to be JX sub M, where the M stands for magnetizing. And then finally, our last piece of our model is an ideal transformer, because we need this system to step up or step down voltages. So we're going to have an ideal transformer here in the middle. Like so, with a turns ratio of N1 to N2. And I'm using my dot convention, and we're only going to deal with these dots in this particular direction. So this is our model, and as it stands, it can be a bit of a pain in the butt to use. So let's talk about things that we can do to simplify stuff. The easiest simplification that we can make is something that we did with our ideal model, and we can refer impedances to one side or the other side, right? So we can put everything on the primary side or everything on the secondary side. So if we wanted to simplify this model, let's start by looking at things referred to the primary side, okay? So everything that's currently on the primary side is going to stay there. So we're going to have our voltage V1, our resistance R sub P, our inductive reactance JX sub P. I'm going to put this RC and this XM in parallel in a slightly different way. This makes it easier to consider it a single impedance in my book. And now we have to refer our secondary impedance R sub S and X sub S over to the primary. How do we do that? We multiply it by our turns ratio squared. So over here, we're going to have A squared RS in series with JA squared X sub S sorry. And then here is where I'm going to connect my ideal transformer. If there is, I would be happy to attempt to answer it. Sorry, what? What do you mean?
I don't know. The last thing I heard was
So we are referring the impedance RS and XS from the secondary side of the transformer to the primary side of the transformer. In our last class meeting, we talked about how we could effectively transfer a load or an impedance from one side of the transformer to the other side of the transformer by either multiplying by A, which is our turns ratio squared, or dividing by our turns ratio squared. When we're moving from the secondary to the primary, we multiply by a factor of A squared. So that's why when my impedance RS is referred from the secondary to the primary, I have A squared RS. And when my impedance JX sub S is referred from the secondary to the primary, I have J A squared X sub S. Yes, so that is an A squared. And I'm going to call this RS prime and XS prime, meaning that these are simply the impedances that are referred to the primary side of our transformer. A couple of other things here that I can include. We're going to have a current here, I2 prime, that is simply I2 over A. We're going to have a voltage here, V2 prime, that is A multiplied by V2. We could consider a small branch current here, I sub E, as our excitation current. So this is the current that is needed in addition to our primary current I1 in order to magnetize our core and all that kind of good stuff. And then we have a current here, IC, representing our core losses, and a current IM representing our magnetization losses as well. All right. So this is what's known as the primary referred model. Okay, so everything is referred to the primary side. What we're going to do now is we're going to simplify this thing slightly here by saying, why do we even need the transformer at all if we happen to refer any connected load over to the primary side as well? Okay, so what I mean by that is, let's say, let me do this in gray here. That I have some arbitrary load impedance that's connected across the terminals of the secondary windings of my transformer. It's the thing I'm trying to deliver power to, right? Well, if I refer that load as well to the primary side of my transformer, what is the transformer doing? Nothing. We don't need it. And so that's another way that we can simplify things. Okay. So this is going to give us what's called the T equivalent circuit. And it's effectively this exact same thing with the transformer part thrown away. So here's V1. Here's RP in series with JXP. Here's my resistance RC. My reactance JX sub M. Here's RS prime. Here's JX prime, JXS prime, excuse me. My voltage here is simply AV2. My current here is simply I2 over A. And here is my load. referred to the primary side. Where ZL prime is simply going to be a squared times whatever ZL was when it was on the secondary side. Okay. So this is my T model. And it's an accurate model that allows me to not even have to worry about stepping things up and stepping things down. I can directly calculate any power and anything like that that I would want. Okay. Now, we are going to develop one more model, and we use it when our excitation current I sub E is very small as compared to our primary current, which is going to be true for practically any transformer that has a steel core or an iron core. Okay. So in the cases where we have a power distribution or transmission transformer, our excitation current will usually be somewhere in the ballpark of 2 to 5% of our primary current. So it's very small in comparison to our primary current. And in that case, we can effectively just lump all of our series components together. Our model a little bit easier to deal with. So this is what's called the cantilever model. I'm going to give myself enough room here to put everything. Oh, and I should have put I1 here. So my cantilever model is going to look like this. Here is RC. Here's JXM. And then I'm just going to lump together the real parts of my series components and the imaginary parts of my components, such that I will have RP plus A squared RS. And here I will have JXP plus A squared XS. And I'm going to call this resistance REQP, and this reactance XEQP. So we have a lumped resistance on the primary side and a lumped reactance on the primary side. Where this voltage is AV2. And this current is I2 over A. And I'm going to put my load over here once again. So the question was the notation that I'm using here, so I'd like to explain it really quickly. I have REQ because I have an equivalent resistance. That's just all of our series resistors lumped together. And then I have comma P because this is the equivalent series resistance that is referred to the primary side. Similarly, I have XEQ sub P because it's an equivalent reactance, all referred over to the primary side. We could also develop models like this referred to the secondary side, so I will draw them all in just a moment, but I want to give you the names of what I'm going to call these so that when I ask you for them on exams, homeworks, etc., you will understand what exactly it is that I'm asking for. So this is our primary starts with a P, not an R. This is our primary referred model. We are going to call this guy right here our primary T model. And this guy down here will be our primary cantilever model. So really quickly, I'm just going to go through and draw our models, equivalent models where everything is referred to the secondary side. Okay. All right, so our secondary referred model is going to be this guy. Yeah. So this is going to be I1, and I'm going to use a double prime notation when I refer things to my secondary side. This is going to be V1 double prime, which is just V1 over A. So I'm going to have some resistance here. This is my primary resistance referred to the secondary side. So since I'm referring it to the secondary side, I'm dividing by a factor of A squared. Whereas when I was referring to the primary side, I was multiplying by a factor of A squared. This is going to be J X sub P over A squared. My shunt impedances were also referred, so I'm going to have to divide them by a factor of A squared. So this is going to give me R sub C over A squared, J X sub M over A squared. My secondary terms didn't get referred or moved, so they're just going to be RS in series with JXS. Here's the quantity V2. Here's the quantity I2. If we wanted to look at our currents, our excitation current, since it's referred from the primary to the secondary side, it's going to have a value of A times IE. Our core loss current is going to have AIC. Our magnetizing current will be AIM. Let's see. And finally, in the event that I have some load, my load impedance ZL is just going to be ZL because it did not get referred to the opposite side of the transformer. So this is my secondary referred model. And then I can certainly eliminate my transformer, which will give me my secondary T model. Oh, actually, let me do one other thing here just really quick. So let's call this RP double prime XP double prime. We could call this RC double prime, and we could call this double prime. Yes, ma'am. Excitation current is the one with a lowercase e, and so that's just it may be hard to see that it's a lowercase e, but this guy right here is supposed to be lowercase e. So the excitation current is composed of both the magnetization current and the core loss current. So that's the current in addition to the primary current that causes this dividing to work correctly. Okay. for here, I was just illustrating that since the impedances that we're dealing with, where those currents exist, were referred from the primary side to the secondary side, we have to scale them by a factor of the turns ratio as well if we wanted to use them for anything. Okay. So when they're on the primary side, they'll be scaled by a factor of A, or excuse me, when they're on the secondary side, they'll be scaled by a factor of A. When they're on the primary side, they won't be. Okay. All right, so our T model is effectively the exact same thing that we have here. We're just throwing away the transformer because we no longer need it. So we're going to have V1 double prime, which is just V1 over A. Here's RP double prime, JXP double prime, RC double prime, JXM double prime, RS, JXS, secondary voltage V2, a secondary current I2, and then taking into account the existence of some load. We just have this guy ZL. So once again, this is our secondary T model or equivalent circuit. And then lastly, under the same assumption here that our excitation current is much smaller than our primary current, we can have a cantilever model where our cantilever model give myself enough room here. So this is going to be RC double prime, JXM double prime. And it doesn't look like I gave myself a lot of room here, but I'll make it work. This resistance is going to be RS in series with RP double prime. So that's going to look like RP over A squared plus RS. Similarly, we're going to have JXP over A squared plus XS here. And we're going to call this REQS. We're going to call this XEQS. Equivalent resistance referred to the secondary side, equivalent reactance referred to the secondary side. Here's our voltage V2. Here's our current I2, and once again, if there's a load involved, since it wasn't referred, we don't have to scale it by a factor of A squared. So this is our secondary cantilever model. All right. So let's look at an example here. let's say that we have a 20 kVA, 8,000 to 480 volt RMS distribution transformer. Has the following resistances and reactances. Let's say that RP is 32 ohms, RS is 50 milliohms, RC is 250 kiloohms, XP is 45 ohms, XS is 60 milliohms, and XM is 30 kiloohms. One thing I do want to point out, so our shunt pieces should always have pretty large impedances, probably on the order of kiloohms, because if they're small, that means we have a very inefficient transformer, right? Similarly, our series pieces should usually have relatively low resistances on the order of ohms to hundreds of ohms, because if they are any larger, we also are going to have an inefficient transformer, all right? So what I want is for us to do our cantilever equivalent circuits, referred to the primary side and the secondary side. Pretty straightforward things. So you guys tell me, let's start with our primary. So we are going to have RC JXM and this is going to be REQP and JXEQP. So let's start with the easy things. What's RC? What's our core resistance, our shunt core resistance referred to the primary side? It's just RC. It's just the 250 kiloohms we were told. Okay. Because that particular piece of information, unless specified otherwise, is always referred to the primary side. Similarly, our magnetizing reactance X sub M is just going to be whatever the X sub M is that we were told. So 30 kiloohms, right? Nothing particularly difficult about that when we're looking at things on the primary side. Now, what about REQP? Absolutely right. So what's that going to come out to be? We've got calculators, let's use them, right? So 32 plus, so what's A? Right. So we're going to have, 32 ohms plus, so what's our turns ratio in this case? 8,000 over 480. Squared times 0.05 ohms I get 45.889. Oops, anybody else get something different? All right. Nobody's saying anything, so let's move along to XEQ for the primary side. So what's that going to be? Pretty much the exact same equation, except I put X's instead of R's, right? So it's going to be XP plus A squared XS. So that is going to be 45 ohms plus 8,000 over 480 squared times 0.06 ohms. I get to be 61.667 ohms, and then we would just replace those symbols with these numbers and our equivalent circuit is done. Nothing particularly wild or crazy here, right? So if we want our secondary cantilever equivalent circuit, what are we going to have? It's effectively going to look exactly the same, except that we are going to have secondary referred things, right? So let's draw this here. So this is going to be RC double prime. This is going to be JXM double prime. Then we're going to have REQS in series with JXEQS. So what is RC double prime going to be? Absolutely right. RC over A squared. So that is going to be 250 kilo ohms times 480 over 8,000 squared. I get to be 900 ohms. XM double prime is just going to be XM over A squared. So that is 30 kilo ohms. $480 over 8,000 squared. For 108 ohms. And then I have REQS, which one way to do this would be RP over A squared plus RS. But I would argue, not 100% sure on this, but in my head it makes sense, that this is just REQP over A squared. I'm going to find out here really quickly, just to cover my butt. So RP, let's see what that was. 32 times 480 over 8,000 squared plus 0.05. So that looks like 165 milliohms if I do it the first way. Let's just check here, 45.889 times 480 over 8,000 squared. Yep, same thing, either way. So if we have the primary, we can just refer it to the secondary by dividing the factor of a squared. So either way works. So let me numerically write this down. 45.889 ohms times 480 over 8,000 squared is 165 milliohms. Yes, ma'am. I didn't really turn it into the second equation so much so as I know that what my primary voltage, excuse me, my primary referred equivalent resistance was. And usually if I have a resistance on the primary side and I want to refer it to the secondary side, I divide it by a factor of a squared. So let's do some algebra here and let's potentially prove this out just really quickly, right? So REQ P is equal to RP plus A squared RS, right? So I am positing that REQS is just going to be REQP divided by a factor of A squared. So if I substitute in what I have, that's going to look like RP plus A squared RS divided by A squared, which is the same as RP over A squared plus RS. So I can do it the long way, or I can take the information that I got in the previous step and do slightly less math by just referring that resistance to the secondary side. Okay. So I thought it would work out, but I haven't done the algebra before right then. And then lastly, we have XEQS. So by the same token, XEQP over A squared is going to be 61.667. And then 480 over 8,000 squared is 222 milliohms. All right. So referring things to the primary and secondary side, relatively straightforward. Now let's talk about how we measure these quantities, okay? If you guys go get a transformer from Dr. Hall's office or something like that, and you weren't there when it's made, you probably don't have any idea of what the real geometry of the core is, stacking factor, or anything like that. Nothing to where you could directly do some math and figure out what any of these parameters are. So it's important that we understand how these are tested in practice to determine their parameters. Okay? So there are two tests that are carried out. We have an open circuit test and a short circuit test. Now, I want to say something here because the book that we are using, the official textbook for this class, in the practice problems and things like that it gives, effectively everything is referred to the primary or high voltage side. That being said, in actual industrial practice, the open circuit test is usually performed on the low voltage windings, and the short circuit test is usually carried out on the high voltage windings for safety reasons, okay? So I'm going to work an example under that constraint, and we're going to talk about things when we derive it. And then I just want you to be aware that a homework problem or something like that I'm going to give you straight from the book might be slightly different. And so I want to talk about where those differences are going to come in. Okay. All right. So let's talk about the open circuit test first. So the open circuit test is performed by applying rated voltage to the LV. So that's going to be my low voltage windings of the transformer. And we're measuring the RMS value of the input voltage and input current while also measuring the input average power, okay? So that means in order to carry out this test, you need a voltmeter, an ammeter, and a wattmeter, okay? 3 pieces of measurement equipment, all right? So the test setup would look something like this. Over here, we apply rated voltage. And we're doing this on the low voltage side. So just for the sake of example, let's say that we have a 2400 240 transformer. We would apply 240 volts because that's the rated voltage for the low voltage side, okay? Directly in parallel with our source voltage, we are going to have a voltmeter. And the voltmeter is going to measure what we're going to call the open circuit voltage. Our voltmeter isn't going to give us a phase angle or anything like that. It's literally just going to give us the RMS value of the voltage. So that's what I'm putting here is what's being measured. The magnitude of the open circuit RMS phasor voltage will just be the open circuit voltage that we're measuring. And in line, we are going to have an ammeter. That is going to measure our input current. So this is going to be the magnitude of our open circuit current. And then we have our wattmeter, and the traditional symbol for a wattmeter is this thing right here. Plus W, and I'm going to put a circle around it because this whole apparatus is our wattmeter. And then finally, way over here is our transformer connection, right? So here is the low voltage winding. This is the high voltage winding, and we're going to leave the high voltage winding open circuited, okay? So effectively, our voltage here, I'm just going to call this V high voltage. We don't have any load or anything like that, so this is going to be approximately equal to N high voltage over N low voltage times our rated low voltage, right? Not particularly important here, just talking about, because we're going to be referring things back and forth and all that kind of things. Okay. All right, so this is what our measurement circuit schematic is going to look like. Okay, so we are effectively using the system to measure three pieces of information: our open circuit voltage, our open circuit current, RMS values, and then the average power that is being delivered to our transformer. Okay, so from a circuit analysis perspective, this is effectively what we have. We're applying whatever our rated voltage is. Don't know what the heck just happened there. Since a voltmeter has nearly infinite impedance, it's going to look like an open circuit. And so we're just going to be measuring this quantity, VOC. Our ammeter has an incredibly small impedance, so it's going to look like a short circuit. So we're going to have a short through which we measure some current, IOC. Then, using our cantilever equivalent model, we're going to have RC in parallel with JXM. And then over here, we're going to have some equivalent resistance, some equivalent reactance, JXEQ. And then our high voltage side is open circuited. I'm being careful here not to say primary or secondary, because any of these transformers, the low voltage could be the primary or the low voltage could be the secondary here, okay? Typically speaking, when we have problems and all that kind of stuff, since like in our example problem up here, we've called this a 20 kVA 8480. The high voltage side would be considered the primary and the low voltage side would be considered the secondary. But I don't want to get too confusing here, so that's why I'm just using low voltage and high voltage, and we're going to have to talk about where we're referring things and where they would normally appear. Okay. Yes, ma'am. Mm-hmm. High voltage. So VHV is approximately equal to NHV divided by NLV times VLV. Effectively, I'm saying that the voltage, the open circuit voltage, be about the turns ratio times the voltage at the low voltage side. So the transformer is stepping it up. Okay. Sorry, indicating here, because I realized I had missed it, that our watt meter is measuring the quantity P open circuit. So, all right, so let me ask you guys possibly an odd question, but what parameters do you think the open circuit test is going to give us? So it's going to give us the shunt components, okay? And the reason why I say that is because if we have our high voltage side open circuited, if we look at our model right here, the resistance REQ and the reactance JXEQ aren't part of a closed current carrying circuit, so they're not going to actually contribute anything. So the quantities VOC, IOC, and POC are going to be used to tell us what RC and XM are. So our open circuit test gives us our shunt or our parallel pieces of our model. And then we're going to see that our short circuit test gives us our series components for our model. That's why there are two tests. One gives us one piece of the information, the other gives us the remaining pieces of the information. Okay. All right, so what can we say about this system? All right, and I'm skipping literally 2 pages of algebra to just give you the results because none of you guys want to suffer through that. I didn't particularly want to either, but I didn't trust the textbook. So by definition, impedance, ZOC, so this is the open circuit impedance, is going to be the ratio of the open circuit voltage to the open circuit current, because impedance is always the ratio of phasor voltage to phasor current, right? But we can see by inspection that the impedance seen by our voltage source is just RC in parallel with JXM. So we're going to have RC multiplied by JXM divided by RC plus JXM. And by doing a whole heck of a lot of complex algebra that I'm not going to make you guys suffer through, what we will find is that our resistor RC turns out it's only the voltage that's measured by our voltmeter squared divided by the power that's supplied by our wattmeter. So what our measurement is on our wattmeter. Okay. Similarly, our magnetizing reactance, X sub M, is going to be this guy. 1 over the square root of the magnitude of our open circuit current divided by the magnitude of our open circuit voltage squared minus 1 over RC squared. So we can determine what RC and XM are just by reading our measurement instruments. We don't have to do any extra work or anything like that. The only thing that I want to point out is that these quantities are referred to the low voltage side of the transformer. Right. So we have to be careful about what we have here. The reason why I say that is because typically speaking, if our high voltage side is our primary, then we would need to scale these by a factor of A squared to refer them from the secondary to the primary for our normal model. Okay. So now let's look at our short circuit test. Let me do this on a new page. Actually, have I given you guys time to write all this crap down? Or are you good? All right.
Got a notation question.
Sure.
For voltage and current, you've got the AC line over it. Is there a reason for power?
So power is always so this is the average power, right? So that's a constant quantity. So the power that's measured by a wattmeter is just going to be a constant thing. So just to be ludicrously clear here and how I derived all this, because I didn't trust things, I'm not going to go through it here. As I said that the complex power absorbed by our impedance there, SOC, and I use a bar for complex power, is VOC times IOC conjugate. So the squiggles over the open circuit voltage and the short circuit current, that's my way of saying we're dealing with RMS phasors. Because whenever I, as an electrical engineer, deal with complex power, I'm always using RMS quantities. And luckily enough for us, that's what our voltmeters and ammeters give us when we have an AC system. So I'm just trying to put things in terms of what we would actually measure. Notation wise, average power, since it's purely real. Actually, none of the portions of my power are going to have a bar over it. Actually, let me put that. Think about another way to put that. So I would say that SOC is equal to POC plus J QOC for my real part, my imaginary part of my complex power. That's the notation that I would personally use. But if you have any questions about how I notate stuff, please ask and I'll happily try to explain it. Because I understand I very likely do things differently than the other professors that you've had doing this crap. So any other questions before we knock out short circuit power or short circuit measurement? All right. So our short circuit measurement is going to be very similar. So the short circuit test is performed by applying a reduced voltage. I can't give you a specific value for that voltage, and we'll talk about that in just a moment. Across the high voltage windings of the transformer. Such that rated current flows through the low voltage winding. Which is short circuited. So to represent our experiment with a picture here, much like we did for the other one, I'm going to have some reduced voltage source. Typically, this voltage required to drive rated current through the low voltage windings is somewhere between 2 and 25% of the rated high voltage. So for a 2400 high voltage winding, we're talking about 20 volts to 100 volts. Okay. We have our voltmeter in parallel that's going to measure our short circuit voltage. So that's our applied voltage. We have an ammeter that's going to measure some short circuit current. We have our wattmeter again. That is going to measure the power of our short circuit test. And then this is connected to, make sure I've got room here. Our high voltage winding. And over here, our low voltage winding is shorted out such that it is carrying rated current. And I'm going to put a circle around my wattmeter again. So we're still going to be dealing with just 3 quantities, all measured by standard measurement tools: a voltage, a current, and a power. And with our low voltage windings short circuited from a schematic representation, effectively what we're going to have is something that looks like this. So here's our reduced voltage that we are applying. Once again, the impedance of our voltmeter is going to be practically infinite. So we would just measure this quantity VSC. The impedance of our ammeter is effectively 0. So we're going to have this current ISC. Here we have our resistance REQ. Here we have our reactance JEQ. Here's RM. Here's RC. JXM, my apologies. Then here's our short circuit. The RC here and the XM here, these are both referred to the high voltage side. So I'm going to put a little high voltage underneath just to be clear here. But because they're literally shorted out, when we short out our terminals, our low voltage terminals, they don't actually come into play at all. So effectively, in this case, all of our short circuit current flows through that impedance REQ plus JEQ, and that's what's going to allow us to determine those quantities while effectively neglecting our shunt quantities. So in this case, our short circuit impedance ZSC is simply the ratio of VSC over ISC, which is just REQ plus JXEQ. Using complex algebra, REQ is going to be nothing more than the reading from our wattmeter PSC divided by the reading from our ammeter squared. And XEQ is going to be our short circuit measured voltage divided by our short circuit measured current, that quantity squared minus REQ squared. So once we know the equivalent resistance from our meters, we can throw that number in to figure out whatever our equivalent reactance is. To be clear, these quantities are referred to the high voltage side of the transformer. So one last example problem, hopefully fairly quick, and then you can work on the in-class assignment. One last thing here before we do the example problem. We are going to talk about two short new topics on Thursday. No, today's Thursday, right? Next Tuesday's class that will be on the following exam. Okay, we're going to talk about voltage regulation and transformer efficiency. That's it. Then we'll use the rest of the class meeting to review and stuff like that before you take your test on Thursday. So we do have a little bit more to talk about, but it's not a whole heck of a lot. No. So that one, not a 1 on top. All of that is just under a square root sign. Yeah. So for the other one, it was 1 over a big thing under a square root sign. For this one, it's just stuff under the square root sign. All right, so wrapping things up here because I've talked for 82 minutes straight.
Let's say that we have a 50 kVA, 2400 to 240 volts, 60 hertz transformer. Is tested. And the following, stop being weird, computer. Data has been collected, all right? So our open circuit test was carried out on the low voltage side, which is where it's usually done in industry. And the magnitude of our open circuit voltage was determined to be 240 volts RMS, exactly what we would expect because we carry this out at 140 volts RMS. We measure an open circuit current of 6.5 amps RMS using our ammeter, and our watt meter gives us a power measurement of 65 watts. Our short circuit test is carried out on the high voltage side. We have short circuit voltage of 45 volts RMS that's measured when our low voltage windings are shorted. Our low voltage windings, when they carry a rated current, we get 20.833. Excuse me, yeah, 833 amps RMS. And our watt meter gives us a power of 300 watts. And what I want us to do is to determine the cantilever equivalent circuit referred to the high voltage side of the transformer. All right. So anybody have any thoughts? Hit you guys with some equations. What can we glean just from the equations that I gave you? Right. So I would argue that we could figure out what the core resistance is on the low voltage side, just from the data that we're given in the table, right? So from our equation, that is just the magnitude of our open circuit voltage divided by our open circuit power. So that's going to look like 240 volts RMS quantity squared divided by 65 watts. Looks like 36.955 ohms. Nope, that's the wrong thing. Reading my paper wrong. My apologies. 886.154 ohms. Okay. My magnetizing reactance on the low voltage side, again, given by an equation that we just came up with a moment ago. 1 over the square root of our open circuit current divided by or open circuit voltage, that quantity squared minus 1 over RC quantity squared. Substituting in the numbers, this is going to give us that 36.955 ohms of reactance. And both of these are referred to the low voltage side. So since we want things that are referred to the high voltage side, here's the $1 million question. Are we multiplying by A squared or dividing by A squared? From the low voltage side to the high voltage side. We're multiplying. Or multiply by A squared, okay? So RC high voltage is just going to be A squared times RC low voltage, which is just 100 RC low voltage, or 88.615 kilo ohms. And similarly, XM high voltage is going to be A squared times XM low voltage, which is just 100 XM low voltage, and that is 3.696 kilo ohms. Now, from the results of our short circuit test, we can figure out what REQ high voltage is. That is just our short circuit power divided by the magnitude of our short circuit current measurement squared. So that's going to be 300 watts divided by 20.833 amps RMS quantity squared, which I get to be 0.691 ohms. And finally, XEQ high voltage is going to be the square root of, VSC over ISC quantity squared minus REQ high voltage squared. And substituting in my numbers here, I get 2.046 ohms. And then from here, I have everything I would need to just draw my equivalent circuit, my cantilever equivalent circuit, right? All right, so that's enough ranting out of me for today. I have an in-class assignment. So this in-class assignment is actually the one that I was going to give you guys on the Tuesday before we got out for break and all that kind of stuff that I didn't have time to do. Problem 1 is about ideal transformers. I would argue, I mean, you can do it if you want to, but today's class would be focused more on problem 2, which is dealing with practical transformer stuff. So